In this video, we're going to think about heat and work, how chemicals hustle in order to get things done. So we know that systems exchange energy with the surroundings through heat, Q, and work, W, where heat is the flow of energy, due to temperature, and work is a force acting through a distance. Both heat and work are not state functions. This means they are path dependent. If you remember from the previous video, we were measuring the change between these two. Delta E is going to be this. It is a finite value, a state function between the two, path independent. However, both heat and work are path dependent. So the heat can take a meandering path, and so can the work. But the sum of the heat plus the work gives you the change in energy for the system. Once we think about figuring out the change in energy, we need to think about how both the energy, the heat, and the work flow. So the sign of these three values is relative to the direction that the energy is flowing. So if it's leaving the system, it's going to the surroundings. Also, if it's going from the surroundings, it's going to go into the system. So if we look at this table over here on the right, when heat goes into the system, Q is positive. When heat leaves the system and goes into the surroundings, it's going to be negative. It's also negative if heat goes into the surroundings. So it matters, where's the heat going and where is it coming from. For work done on the system by the surrounding is work going into the system, so it'll be positive. The system does work, so the work is leaving, so it's negative. Delta E, the system gains energy, so it's positive. And when energy is lost from the system, it is negative. You can think about this kind of like a gas tank. When work is done by the car, the gas is leaving, and work goes into the car when gas is added back. So it's really important to read really carefully and think about this table as we look at this. So in a potato cannon, so a potato cannon is a PVC pipe where you put a potato inside, you light an accelerant on fire, and then the potato is ejected from this tube. So the burning of the fuel or the accelerant is going to expel this potato. If the burning of the fuel does 855 joules of work and produces 1422 joules of heat, what is delta E for the burning of the fuel? So delta E equals Q plus W. On the surface, this is a really simple calculation. The reality is we need to think about what does Q equal and what does W equal? So the heat is 1422 joules, but it produces this heat. So if delta E for the burning of the fuel, this heat is lost, so it's going to be negative. And the burning of the fuel does work. So in this case, it would be like this one right here. The system, the fuel, does work on the surroundings. So this is also going to be negative 855 joules. So delta E is going to be negative 1422 joules plus negative 855 joules. And so the final value is negative 2277 joules. So with these types of questions, the hardest part is figuring out what is the sign of the value. So let's look at another example. So if the contents of a cylinder examined, this should be expand. The contents of the cylinder expand, pushing the piston out, doing 488 joules of work, and the cylinder absorbs 559 joules of heat. What is delta E? So delta E equals Q plus W. Feel free to look back at your previous slide for that table. And so if we think about Q, where the heat is going to be 559 joules and the work is 488 joules. So this says that the piston does work. So since the work is leaving the system, it's going to be negative, but it is going to absorb 559 joules of heat. So Q plus W is positive 559 joules plus a negative 488 joules. And that gives me delta E is equal to 71 joules. You don't have to write the signs. I always bring them along just to make sure that I can really think about these. If the change in energy is equal to the heat and the work, the other thing we can start to think about is how could we calculate or measure the change in heat or the change in work for any of these given systems. So heat is directly proportional to the change in temperature and the ability of a substance to absorb the heat. So some substances absorb heat readily, others don't. So the ability of a substance or the measure by which it absorbs heat is called the heat capacity. And so heat capacity is the amount of heat required to raise the temperature by 1 degree Celsius or a Kelvin. And the thing is, heat capacity is relative to the amount of substance. If you want to raise 1 gram of something, you need a certain amount of heat. If you're going to raise 1 mole of something by 1 degree, you will need a different value. So the specific heat capacity, C sub S, is the quantity of heat required to raise 1.0 gram by 1 degree Celsius. And so the units of this are joules per gram Kelvin. The molar specific heat capacity, or the molar heat capacity, C sub M, is the heat required to raise 1 mole by 1 degree Celsius. And so the units of this are joules per mole Kelvin. Now, both the specific heat capacity or the molar heat capacity would be provided in a problem or read out of a table, or it would be the thing that you're solving for. So we can calculate the heat required to change the temperature of any amount of substance by using one of these two equations, where Q equals mc sub s delta T, where m is mass, in this case in grams, C sub S, which is the specific heat capacity, and delta T. Or we can look at it for Q in terms of N, where N is moles, and C sub M is the molar heat capacity, and delta T. Just like delta E, delta T is calculated T final minus T initial. Now up here it says by 1 degree Celsius or 1 degree Kelvin. Technically this is in Kelvin. However, if we look at the temperature scales, a change of a delta 1 degree Celsius is equal to a change of 1 degree in Kelvin, which is not equal to a change of 1 degree Fahrenheit. So we do not need to convert to Kelvin at this time in order to subtract the two. If we're going to use the temperature, we would need to do that. So let's look at some examples on how you could calculate heat. Suppose you find a penny in the snow at -8 degrees Celsius, and it warms to body temperature, which is 37.0 degrees Celsius in your pocket. If the penny is pure copper weighing 3.1 grams, how much heat is absorbed by the penny? And C sub S for copper is 3.89 joules per gram Kelvin. So we know we want to Q equals M C sub S delta T. So the mass is equal to 3.10 grams. C sub s came just out of the problem, 0.389 joules per gram Kelvin. And delta T is equal to final, which is 37.0 degrees Celsius, minus the initial, in this case, which is negative 8.0 degrees Celsius. And that gives us 45 degrees Celsius. So now we can plug all of these values into our calculation, where we get 3.10 grams multiplied by 0.389 joule per gram Kelvin, multiplied by 45 degrees Kelvin. And so our units are going to be left with just joules, and this gives me 53.7 joules as a final answer. So we can, for any of these, look at the transfer in a specific element. In this example, we have a 55-gram block of aluminum, and it's going to absorb 725 joules of heat at 27.5 degrees Celsius. If C sub s is equal to 0.903 joules per gram Kelvin, what is the final temperature of the block of the aluminum? So this one is a little different. We're still going to use Q equals M C sub s delta T. Well, we have Q this time. We have 725. And M is 55.0 degrees. Yep, that's 55 grams. C sub s is 0.903 joules per gram Kelvin. But delta T, TF, minus 27.5. So we are looking for TF. So in this case, we're going to solve for delta T, and that's equal to Q over M C sub s. We're going to take our 725 joules, divide that by 55.0 grams, multiply by 0.903 joules per gram Kelvin. So that's going to give us 14.6 Kelvin equals delta T. Well, if delta T is TF minus 27.5, and that equals 14.6 Kelvin, TF is going to equal 42.1 degrees Celsius. And we change the units because we are looking at the delta T. So this, in this case, you do not need to convert both of these answers. So we can also start to think about transferring the heat between two objects. So if we were to have a system in a surroundings, where in the example below, we're going to have a cup of water, and then we're going to drop into it a tiny little cube of aluminum. And so what we need to think about is the fact that the energy that goes from the aluminum to the water is equal to the lost energy from the water. So the Q of the system plus Q of the surrounding, or Q of the system equals negative Q of the surroundings. You can also think about this as Q system plus Q surroundings equals 0. So all of this allows us to think about the movement of energy. So in this example, we have a 32.5 gram aluminum block at 45.8 degrees Celsius, and it's going to be dropped into 105.3 grams of water at 15.4 degrees Celsius. What is the final temperature of both items? C sub s of aluminum is equal to 0.903 joules per gram Kelvin. C sub s of water is 4.184. So I'm going to move this slide up just a little bit so we have a little bit more space. So in this case, we need to think about the fact that Q of the aluminum is equal to negative Q of the water. So in this case, we are going to know that the mass of aluminum times C sub s of aluminum times delta T is equal to negative mass of the water, C sub s water, delta T. So both of these are going to be different, so we'll mark them AL and water. So now we can just identify the values. So the mass of aluminum is equal to 32.5 grams. The C sub S of aluminum is 0.903. Delta T is going to be TF minus 40, hold please. That's going to be 45.8 degrees Celsius. The mass of the water is 105.3. C sub S equals 4.184 joules per gram Kelvin. And delta T is also TF minus 15.4. So now we can just start plugging these values into this equation where we're going to have 32.5 grams multiplied by 0.903 joules per gram Kelvin. And then in this case, I'm going to just leave these as delta T for now. And this is going to equal negative 105.3 grams times 4.184 joules per gram Kelvin delta T. So we can plug these into our calculator and get 29.3 delta T, which is going to be TF minus 45.8. And we're going to get negative 440.6 TF minus 15.4 degrees Celsius. So now, in order to solve for TF, we can multiply the 29.3 over both values and the negative 446. So I get 29.3 TF minus 134.1.9. And that equals negative 440.6 TF plus 6,785.24. Now we're going to group like terms together. So we're going to get 8127.1 is equal to 469.9 times TF. So TF is going to be equal to 17.3 degrees Celsius. So the transfer of energy between these two, all of the heat lost from the aluminum is gained by the water. So in this case, you can start to think about the heat exchange as well. So these calculations have shown us how to calculate for heat. But how could we actually calculate the work done in a system? So work, W, so work is often calculated force times distance. And so in terms of chemistry, we don't tend to add forces in this way. We think about the expansion of a gas. So if we think back to previous videos, we know that when a balloon is blown up, it's going to get bigger. So when it gets larger, it's actually doing work against the external pressure. So we can, at constant pressure, which means on the bench top, work is equal to P, negative P, which is the pressure, times delta V, which is the change in volume. So work is P delta V. And so I'm going to slide this over. We'll slide it back in a second. So if we have work equals negative P delta V, so this would be negative, and the units here are going to be atmospheres. And then we're going to be multiplied by liters. So work needs to have a unit of joules. So if you remember back to the ideal gas constant, we need to use a conversion factor. And we need to figure out how to go from joules to liter atmospheres. So we can use two different R values of 8.314 joules per mole Kelvin is equal to 0.08206 liters atmospheres mole Kelvin. So in this case, we forgot a Kelvin over here, we can actually solve for 1 liter atmosphere by dividing 8.314 joules per mole Kelvin divided by 0.08206. And this is in moles Kelvin or over moles Kelvin. So your moles Kelvin will cancel. So this gives us that 101.3 joules is equal to 1 liter atmosphere. This value will be given on an equation sheet, but I just wanted to let you guys know where it came from. So in this case, it's 101.3 joules is equal to 1 liter atmosphere. So the question, or the example question, asks us, if you blow up a balloon from 0.1 liter to 1.9 liters at a pressure of 1.02 atmospheres, how much work was done in joules? So work equals negative P delta V. So we have a pressure, in this case of 1.02 atmospheres, and delta V is 1.90 liters minus 0.100 liters, and that's going to give us 1.80 liters. So now we can plug in our values. Negative 1.02 atmospheres multiplied by 1.80 liters, and that gives us negative 1.836 liter atmospheres, and it asks for this answer in joules. So we will convert 1 liter atmosphere is 101.3 joules. And so this gives us negative 186 joules. So work is negative P delta V, or the pressure multiplied by the change in volume. So let's look at another example. So when you scuba dive, your lungs are on a constant pressure of 1.65 atmospheres. Each breath requires 865 joules of work, 856.6 joules. What volume of air in milliliters is exchanged in one breath? So in this case, work equals negative P delta V. So in this case, we can determine, in this case, we are looking for delta V. So we have work of 856.6 joules is equal to negative 1.65 atmospheres delta V. So we're going to need to convert joules. So there are 101.3 joules in 1 liter atmosphere. We're going to divide that by 1.65 atmospheres. And this is going to give us that delta V is equal to negative 5.12489 liters. So this asks for the volume of air in milliliters. So we need to multiply by 1,000. And this is going to give us negative 5,124.9 milliliters. So we can only have 3 sig figs. And so we're going to round this value. So it's going to be negative 5,120 milliliters. Now you could have assigned this as a positive value. So the work, each breath requires this much work. And so the work is both leaving the system and going into the system. When you breathe out, you are doing work on the surroundings. When you breathe in, they are doing work on the body. When we can calculate heat and work, this is going to allow us to think about how a reaction functions in this given system.